Okay, this is lesson 11. Lesson 11 is on a half-life of a reaction. This follows on what we did last time, which was on integrated rate laws. Okay, so just a little bit on the schedule. Homework 8 and 9 are due April 29th and May 1st. Next week, which is when some of you will be watching this, May 4th through 8th, we have a quiz on May 6th. We have homework due. 10 and 11 will be due on sapling. Number 12 will decide probably on sapling. There's also a survey. This is on Blackboard underneath the grades on the left-hand side. This is due Wednesday, May 6th. And this kind of goes through, I just want a feedback on how the course is operating, and we can make adjustments if needed. May 11th, test number 2. Okay, so quiz number 2, just a few things. It'll work a lot like quiz number 1, except now it will have 2 to 4 problems on rates and differential rate laws. That's lesson 7 to 8, and then integrated rate laws. That's lesson number 10. Okay, review. Last time we talked about integrated rate laws, and integrated rate laws allow us to relate the concentration to time. And the nice thing about this is, if we were to do different plots, we can tell what type of rate it is, or rate law it is, based on when it has a straight line. For instance, look at this plot. This plot is a straight line. And this only happens when I have ln A versus time. So if you go back, you can see that, okay, the only time you get a straight line for this is if it's a first order reaction. So the differential rate law is this one right here, where I have that the rate is equal to Ka, and notice there's a 1 here. Usually I don't even include it. That means it's first order. The integrated rate law is this one right here. Remember, integrated rate laws are nice because they relate concentration to time. Okay, that's what we don't get with differential. And then, based on this, notice that the K is equal to this slope here, 0.12. And it's going to be in units of seconds to the minus 1 because time's in seconds. All right, so that's what we learned last time in lesson number 10 about integrated rate laws. We went through 0, first, and second order. And in these, we were able to, like we did in the last one, determine orders graphically. We could figure out concentration at any time. But now we're going to look at something called half-life. Half-life, which is represented by T with a half. Okay, this doesn't mean you divide by 2. This just means this is its symbol. It's the time required for half of A to be consumed. Okay, this is important because it's important in a lot of reactions. But for instance, when we're talking about, COVID-19 and how long it stays on surfaces and all these things, one of the things we're looking at is the half-life. What this means is that on stainless steel, if I have 2 viruses on, or 100 viruses on there, 5.6 hours later, I'm going to have half as many. 5.6 hours later, after that, I'll have half as many. Whereas copper, right, notice its half-life is smaller, 0.7 hours. So actually, that means that the COVID actually dies quicker on the copper. Okay, so let's go ahead and let's figure out how we determine half-life. Okay, so half-life is the time required for half of A to be consumed. So what that means is that at the half-life, T half, the concentration is equal to half of what it was initially. Remember, for initial concentration, we put this, A naught, meaning concentration in time 0. Okay, so we're going to go ahead and we're going to find first half-life for first, second, and zero order. We're going to start with first order because this is the most important one. Okay, so remember what we said. Ln A T equals negative KT plus ln A naught. Okay, this is a first order integrated rate law. So I'm going to go ahead and plug these things in. So ln of 0.5 times A naught, I'm plugging this in for here, equals negative KT plus ln A naught. I can move this over such that ln of 0.5 A naught minus ln of A naught equals negative KT. I can, and now seeing that this is half-life, if I'm looking at the half-life, I can just replace this T with T half. I can rearrange this such that it's ln of 0.5 A naught over A naught equals negative K T to the half. Okay. This is a law of natural logs and also logs that you can do this. Notice these will cancel out and I get ln of 0.5 equals negative K T to the half. Okay. I can then, because this is negative, I can actually make this ln2. Right? This is actually 1 over 2. So if I make this negative and negative, this becomes ln2 equals K T to the half. Okay? You don't get that all, that's not as important, but what's important is I can now rearrange this to get my half-life is equal to ln2 over K. So what this means is if I have the half-life, okay, or sorry, if I have the rate constant K, I can plug it in here and I can find my half-life. Okay. So for instance, by the way, ln2 is 0.693. What does this mean? What this means is that, notice how this half-life is the same no matter what the concentration is, right? Concentration isn't in this. So what that means is that if I start off with 1 molar, one half-life later, I'm going to have half. Then 1 half-life more than that, I'll have a quarter. Then 1 half-life more than that, so 3 half-lives, I'll have an eighth, etc. Right? So it's constant throughout. So what I get is kind of this slope down. This is what we call an exponential decay curve. This is what happens in nuclear waste. Okay? Now, also look at it. K is on the bottom, and K tells us about the rate, right? So a big K means it's a fast reaction. And if it's a big K, that means it's a fast reaction. And seeing that K is on the bottom here, that leads to a small half-life, right? So the faster the reaction, the smaller the half-life. All right, let's go ahead and let's look at zero order. All right, so for zero order, I'm going to start off, sorry, I need to find my eraser, took me a little while. I'm going to start off with the same thing, except for zero order, remember A times T equals negative KT plus A naught. So if I plug in this information, I get A 0.5 times A naught equals negative KT, this is now half-life, plus A naught. I can move this over here. This is going to get me negative 0.5 A naught equals negative K times half-life. Going to make this positive, this positive. And now I'm going to go ahead and rearrange this, right, by dividing by K. That's going to be 0.5 A naught over K equals my half-life, or half-life equals A naught over 2K. And this is my half-life now if I have a zero order reaction. Notice that it includes concentration. What that means is when I have it on here, it's going to vary based on my concentration. So it's not going to be constant, right? In first order, it was always the same. But once it's zero order, the half-life is going to vary based on my concentration. So it may be 10 seconds at the beginning and then less as we go on. Okay, now let's go ahead and let's look at second order. Okay. So for second order, remember, we had a slightly different one. We had 1 over A at t equals kt plus 1 over A naught. If I plug in this information, I get 1 over 0.5 A naught equals kt plus 1 over A naught. I can move this over, so I get 1 over 0.5 A naught minus 1 over A naught equals kt. I can then notice how I can't just add these because the denominator is different. So I need to make those denominators the same. So I'm going to do that by multiplying this by 2 over 2. So that gets 2 over A naught minus 1 over A naught equals kt. By the way, this is now half-life. Seeing that I have said this is at the half-life. Okay? And now I can go ahead and I can say this is 1 over A naught equals k to the half, or my half-life is now 1 over k A naught. Okay. This is now on the screen. And now notice again that it includes my concentration. So what that means is that it's going to vary during a reaction, right? My half-life's not going to be constant. Okay? All right. Okay, so now let's go ahead and do a reaction. Or let's do a problem. All right, so notice how on top here I have all 3 of those, 0, first, and second order. Right? We only care about the first order. Right? We're only going to use the first order because notice how the other ones vary with concentration. Right? So we're only going to do the first order because that's the more important one. Okay? So let's say we have a first order reaction and we're given a K of 25 seconds to the minus 1. And K equals 25 seconds to the minus 1. And we want to know its half-life, t to the half. Well, we can just use that equation, ln2 over K, plug in for my K, and now I go ahead and I get I do this, I get 0.028. Notice this is in seconds to the minus 1, so 1 over seconds to the minus 1 gets me seconds. So what does this mean? This means that this is a very short lifetime, right? This means that if I start with, let's say, 20 grams of the substance, or let's make it 2 molar, 0.028 seconds later, I'm going to have 1 molar. 0.028 seconds after that, I'm going to get 0.5 molar. So this is going to go away very fast, right? So after 5 seconds, I'm going to have a very, very small amount. Okay? All right, so that was for something with a K of 25 seconds. Why don't you go ahead and figure it out if I have, instead of that 25 seconds to minus 1, my K is much smaller, 0.0025 seconds to the minus 1. Okay, so that's video problem 11A. Now let's expand on this one more time. And for that one right there, we use K to figure a half-life. Let's say we have something else, right? Let's figure out another way to figure out half-life. So let's say we do some data, right? So we're looking at the first order decomposition of H2O2 in water at 40 degrees. And we have this data. We start off with 1 molar. That's at time 0 seconds. Then at 0.5 molar at 2.16 times 10 to the 4th seconds. That's 6 hours. And then 0.25 molar, etc. So let's do this on the board. Okay, so let's do this problem. So we have that it's first order. That means that T half equals ln2 over K, right? The natural log of 2, that is. So we want to figure out the half-life. So let's look at this, right? We start off at 1 molar, then we get to 0.5 molar. That's half as much. So the time required for that, that's my half-life. So my half-life is 6 hours. Or, if I look at it, it's 2.16 times 10 to the 4th seconds. Okay? These are both my half-life. In the same way that how long have I been speaking? 13 minutes. Or I could do 13 minutes times 60 seconds and say it in seconds. All right, so which one I use kind of depends on the circumstances, and we'll talk about that in a little bit. All right, so in B, if I want to figure out K, I can use this equation. Notice previously we used K to find half-life, but now I could rearrange this and say that K is equal to ln2 over my half-life. So this is now ln2 over, let's use 6 hours. Okay. ln2 is 0.693. That will get me 0.11, let's go with 6 hours to the minus 1. Or I could say this in seconds. And this is going to get me a small number, 3.21 times 10 to the minus 5 seconds to the minus 1. Both of these are my rate constant, okay? In the same way that I can talk about, going 22 miles per hour, or I could calculate how many miles per minute that would be, right? 60 miles per hour is 1 mile per minute, right? Those are the same speed. Right? These are the same K value. Okay. Now, we could actually, once we find K, we could use the rate order or the rate law to figure out the concentration at any given time. And this is actually what you'll do in video problem 11B, right? Here we're told what the half-life is. We need to find K, and then we want to know the concentration later so we can use the first order integrated rate law. That's what we dealt with last time to figure out the concentration. Okay, so half-life. Half-life is really important. It's the amount of time required for half of A to be consumed, right? For instance, if I had H2O2 in water, that's hydrogen peroxide that we were just talking about. Its half-life is 6 hours when it's at 40 degrees, right? This is what we've been talking about in this problem right here, okay? Well, if I go to a higher temperature, that half-life actually gets shorter. The reason being is that the reaction becomes faster. So the higher the K, the smaller the half-life. Here are two kind of extremes, right? So OH is what we call radical. It has an unpaired electron. In the atmosphere, it has a half-life of 10 to the minus 9th seconds. What that means is that it reacts almost immediately, right? 10 to the minus 9 seconds after I have some, half of it decays away. And on the other side, 234 uranium, this is one of the things we use in nuclear energy, it has a half-life of 245,000 years, right? That's because this is a slow reaction, okay? So a small K means it's a slow reaction, which means it has a large half-life, okay? A large K means it's fast, and that means it has a very small half-life. Okay? Now, things that have very long half-lives, we don't usually use it in seconds. Now we talk about it in years, right? So for instance, that 234 uranium, it lasts for a long time, right? And there are other radioactive waste that takes a long time. And this is one of the things that we have to worry about when we deal with things like nuclear energy. What are we going to do with all that waste for 245,000 years, right? I don't plan on living that long, maybe only 100,000 years. So what are we going to do after that? One thing, I just found this interesting. This is an article from Financial Times. And they were talking about what do you do if, let's say, you had a whole bunch of waste and you wanted to keep it. Well, who knows, in 245,000 years, they may not be speaking English, right? They may be speaking Neptunian for all we know, right? So let's say you had some nuclear waste. One thing you could do is, instead of having just signs that say, nuclear waste, don't dig, maybe you just put a bunch of spikes around, right? If you see all these spikes, you may know, hey, something looks wrong. Maybe I'm not going to do it. Another thing they said was maybe we'll put a whole bunch of these types of paintings by Edward Munch, the Scream ones, just to show that, hey, you know what? Something's not right. You don't want to be here. Another example they said was, this is something like, what if you put a whole bunch of genetically modified trees there, right? That basically said, hey, this is a place you don't want to be because there's nuclear waste. All right, so that is it for half-life. It's a short section, but we're actually going to spend a little more time reviewing kinetics while we're here, okay? So a half-life is the amount of time for half of A to be consumed. We really only care about first order, right? That's because 0 and second order, you have more variable ones. Okay, so let's go ahead and let's just do a quick review of kinetics. We're going to talk about 0 order, first order, and second order. And we're just going to talk about, hey, what are the differences in rate laws, etc. with these, okay? So 0 order. 0 order, we have, for our differential equation, we have that rate equals K. It's actually K A to the 0, but because it's A to the 0, we don't even include it. That's the differential rate law, okay? It relates rate to concentrations. The units for K are in molar per seconds. The integrated rate law. The integrated rate law we learned last lecture is A equals negative KT plus A naught. Okay. This is integrated rate laws we see, or 0 order we see a lot when we're talking about catalysts. Now, this is an equation of the line. So if I graph concentration versus time, I'm going to get a straight line where the slope equals negative k, and my y-intercept, that's my initial concentration. All right, the half-life for this, we have an equation, but we don't really care about it. Okay, let's go on to first order. First order are really important. This is what we see in exponential decay or nuclear waste. We see this in catalysts as an example. Okay, its differential rate law will be rate equals K times A to the 1, hence first order. Its integrated rate law will be ln A equals negative KT plus ln A naught. And so if I plot ln A versus time, I get a straight line, again, where slope equals negative K, and I get a y-intercept that equals ln of A naught. We learned that the half-life for this is equal to ln of 2 over K. This one you have to know, and you need to know how to use, hence today's lesson, because this is constant, right? It doesn't depend on the concentration. It only depends on K. All right, the last one we're going to talk about, second order. Okay, second order reactions, these are what we see in what we call self-reaction. Right? That's when one reactant or one compound reacts with itself. Okay? So this is rate equals Ka squared. Its integrated rate law is 1 over A equals Kt plus 1 over A naught. And notice that this one, now if I plot 1 over A versus time, now I get something where the slope is just equal to K. These are negative K, and hence why the slopes are going down. This has a positive slope, and this is just slope equals K. And this y-intercept, this is 1 over A. Okay? The half-life for this, we don't really care because it varies depending on the concentration. Okay, here's that on the screen again. You should know how to do this and understand it. One last thing we should talk about is notice how here I have plotted concentration versus time. That gets me a straight law for zero order. ln A versus time gives me a straight line for first order. 1 over A versus time, that gets me a straight line for second order. Okay? But what if I were to just plot concentration versus time for all of them? Right? Well, for my zero order, I get this, but then eventually it gets to 0, and then it flattens out. That's because I can't get negative concentrations. First order, it just decreases with time, but it never gets to 0. But it's not a straight line. And for second order, I get something similar, but it's a slightly different curve. Okay, so that, zero order, we get variable half-life. It does reach 0, and it has a constant rate. First, it has a constant half-life. It'll never reach 0, and its rate is variable. And then second order, it has a variable half-life, never reaches 0, and variable rate. Okay, so that is it for lesson 11. Remember, the homework for this is due next Wednesday. That's May 6th, and it's going to be through sapling. All right, talk to you later. Bye.